All right, so second part of 15.5, we're going to talk about normal vectors and surface area of parametric surfaces. So we actually have to do some math now with parametric surfaces. All right, so back in chapter 14, we came up with a method of finding surface area, the surface area of surfaces. We used a double integral to find the surface area. So if we had a function, just as a reminder, if we had a function equals z equals f of x, y, and we said our surface area was the double integral over our region of ds, where ds was the square root of f sub x squared plus f sub y squared plus 1 dA. So this is how we found the surface area of a surface defined explicitly, z equals f of x, y. And if we remember, our formula came from looking at the approximating a little element of surface area on our surface with the tangent plane. And then we summed the little areas of the little parallelograms or little rectangles that the tangent plane approximation gave us over our region. So we're going to do a similar thing with parametric surfaces. So let me draw a picture, and I'm not going to go through the same argument again, but I'll draw the picture that we're talking about just to develop our formula. So we have our axes. And we have a surface up here. Oops, here's our surface. And we have, our surface is a parametric surface, so we have some r of u and v is our surface. And what we're going to do is look at along this, we're going to assume that along this curve that u is constant, and along this curve v is constant. So we can draw some tangent vectors and use those for our approximation. So let's draw, I'm going to draw a tangent vector in here. Or sorry, not a tangent vector. That's going to be our normal vector. And let me do my tangent vectors in blue. So this is our tangent vector this way, and we have a tangent vector this way. And this tangent vector is given by r sub v. And this tangent vector is given by r sub u. And our normal vector is given by the cross product. Our normal vector is a cross product of these two partial derivatives. And what we did was we approximated the little element of surface area with the magnitude of this cross product. We said the magnitude of the cross product is the area of the little parallelogram with r sub u and r sub v as the sides. So these are our tangent vectors. Normal vector is given by their cross product, and our little increment of surface, little element of surface on our parametric surface our element of area is going to be the magnitude of the cross product times delta u delta v. And the area of the surface is going to be the sum of these tiny little pieces of area over the entire surface. So we can say that the area of our parametric surface, that our total area is going to be the integral, double integral over our region of the magnitude of r sub u cross r sub v times du dv. And we could also write that as the double integral of the magnitude of the normal vector. And if our parametric surface is given by this explicit equation, z equals f of xy, then our parametric surface is just xi plus yj plus f of xy k hat. And our surface area integral, this cross product or this normal vector, is going to reduce to what we wrote before for the area of our surface. So if we let this be our parametric surface, we get the equation for the surface area that we came up with before. And we're assuming here that our surface is smooth, and that means that our cross product doesn't equal 0 on the surface. So Ru cross Rv doesn't equal 0. So we're just working with a parametric surface where our functions are well behaved, essentially. So now we have we talked yesterday about how we come up with a representation for a parametric surface, what a parametric surface looks like. Now we have a tool for finding the area of a parametric surface. We can also find the equation, the equation of a tangent plane to the parametric surface. So at a point, we can find a normal vector here, and the normal vector gives us our direction numbers for our tangent plane. So we can write the equation of a tangent plane at a point for a parametric surface. And the normal vector of a surface is going to play a big role in what we do at the end of the chapter. Questions? All right, let's look at a couple of examples of calculating with parametric surfaces, a surface area, and a tangent plane problem. And that's all we're doing today. Not all Calc III. I don't think at UCD I don't think they do a lot with parametric surfaces. So I just wanted to touch on them a little bit so they have some little bit of familiarity with them. So we want the equation for this example. We want the equation of the tangent plane to our surface R of u and v. Ui plus v j plus square root of uv k at the point 1, 1, 1. So here's our surface. If we were to write this in rectangular coordinates, we would have z equals the square root of xy. So that would be our surface. To find our tangent plane, we need a normal vector. So our equation for a tangent plane, we need a normal vector. So our normal vector is given by our cross product, r sub u cross r sub v. So we need to calculate some partial derivatives. So the partial of r with respect to u is what? I hat. Okay, so 1/2 v square root of uv. Negative 1/2, right. Okay, and that's our k component. R sub v is j, and then 1/2 u uv to the minus 1/2 k. And we need to do our cross product. So we'll represent our cross product with our determinant. So we have 1, 0, and v over 2 times uv to the minus 1/2 here. And we have a 0, 1, and a u over 2 times uv to the minus 1/2. And when we do this cross product out, we get, I'm not going to go through the procedure, but we end up with minus v over 2 square root uv I minus u over 2 square root uv j hat plus k. So that's our cross product, and then we want our tangent plane at 1, 1, 1. So at 1, 1, 1, we have minus 1/2 I, minus 1/2 j, plus k. So this is our normal vector at our point. So this gives us our direction numbers. So if we want to, thinking back to how we write our equation of a plane, so I'm just going to write our direction numbers. A equals minus 1/2, B equals minus 1/2, and C equals 1. And our equation of our tangent plane is going to be, let's see. So this was Is this going to be diamond R? Our equation of our tangent plane, right? Our symbol that we came up with.
I really like it. You should
So maybe since we have a parametric surface and this is a vector, maybe it should be diamond dot R, right? So we have a scalar. Yeah. So yeah, what the? We invented some mathematical symbols last year.
We're using it next year, the diamond thing.
Yeah,
Yeah,
definitely.
like the class last year came up with this, and we're just really trying to make it big. It's like that book
Yeah.
Frindle. What? It's like this kid started calling pens Frindles, and then after 10 years or something, the dictionary knows like Frindles. Super cool. Yeah. So we can.
Wait, what does the diamond mean again? I don't know.
Tangent plane. So this is our equation of tangent plane. So this is our equation, z minus 1 equals 0. So we do x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. That's our equation of our tangent plane. And just as a heads up, for the final, we talked about some vector stuff at the end of second semester. That is normally in first semester of Calc III. So some of that stuff will be on the final. There's like calculating dot products, calculating cross products, some of that stuff that we did right at the end of second semester. We've been using it all semester. So these things like writing the equation of a plane, those kinds of things. But that they do show up on the UCD final because they don't cover them until second semester. But we'll talk about that more as the final gets closer. So there's our equation of our tangent plane at the point 1, 1, 1. Questions on that problem? So our normal vector is just given by the cross product of our partial derivatives with respect to u and v. And then we just need to remember how to write the equation of a tangent plane. All right, so let's do a surface area calculation, and we will be done. So we want to find the surface area. Surface area of R of u and v, our parametric surface, is u square root of u cosine v I plus the square root of u sine vj plus uk. And our interval is 0 less than or equal to u less than or equal to 4, and 0 less than or equal to v less than or equal to 2 pi. So what we're looking for, our surface area